Hello, everybody. Hi. My name is Masha. Some of you may have met me already as part of office hours and seen me post on Ed and things like that. I'm really excited to be giving the lecture today. It's going to be in a slightly different format than Tengyu's or Chris's. So feel free to give me feedback on that afterwards on Ed or by email, whatever you like. But the topic today is actually kind of fun. So we're going to start our foray a little bit into deep learning, so neural networks. I'm assuming everyone here has heard of neural networks before. Anyone who hasn't? Yeah, that's what I thought, pretty much. So it'll be fun to see how the ideas of what's happening in the state of the art actually come back to all the things we've been talking about so far. So ideas in linear regression, ideas in logistic regression, all of this will connect to how neural networks work. So before I get into the mathy, notation-y type of material, I wanted to start with some motivation. Who here has heard of GPT-3? Yeah, a lot of you. So it made big waves a couple years ago. It was a huge, huge model, but it was able to do really impressive things. Like in this case here, it came up with a poem on its own, right? And the hope is that these deep learning models learn to be so expressive that they can do creative things like creative writing. More recently, this was very, very recent. Has anyone heard of DALL-E 2? A few of you, yeah. So this is very, very recent. And so DALL-E 2 is able to generate images. And the prompt here is an astronaut riding a horse as a pencil drawing. And you can see the main one that I picked out and then a bunch of different versions of what else it can come up with. So deep learning is very, very powerful, for better or worse. But it also has so much potential to do such amazing things, right? Obviously, this is cool, but there's also applications in medicine, applications in education, applications in things like autonomous driving, which could hopefully make our roads safer. So there's lots of potential here. And that's sort of the backdrop to where we're going to start. We're going to talk about the origin story of all these things. So we're going to start with supervised learning with nonlinear models. So far, most of what we talked about has been linear models. And now we're getting into the nonlinear territory. And I'll talk a little bit about what that means. And then we'll get started with neural networks. We'll figure out what the heck they are, how we can define them, and next lecture we'll actually talk about how you can optimize them, and I believe Tengyu will be giving that lecture. Any questions before I get started? Cool. All right, so first let's think about linear regression. So we've seen this a bunch. And so we can get started with a data set that we might have, right? So we might have some xi's and yi's. So some inputs and outputs in our data set. And say our data set is of size n, right? And we know for linear regression that we have a prediction that we can make according to something like this. Right? So we have a linear function that we're using to predict. And this function depends on our inputs x. Can anyone help me out with what our cost function might look like in terms of y's and h's for linear regression? Okay, h minus y. Okay. I heard somewhere. Sum over I. Yeah. This looks good to me. This look good to everyone? Familiar? Hopefully we've seen this all before. Awesome. Okay, so we have a prediction here. and we have our label. And what we can do is we can also write this directly in terms of our parameters. So our parameters here are theta and b. Cool, I just plugged it in. Makes sense so far, right? And what we can do is run things like gradient descent or stochastic gradient descent in order to optimize this. Cool? So last lecture, you talked about a slightly different set of models. You talked about kernel models. And so with kernel models, we still have a similar setup, right? So we have our xi's, our yi's. Right? And then what does our h theta of x look like? So what does our prediction look like with kernel models? Does anyone remember from last class? Hint, it's very similar to what we had before.
Zeta transport times Vx.
Yeah. And what's phi of x? Sorry? The feature map. Exactly. So what's interesting about this setup is we're still linear in parameters, right? But we're nonlinear in the inputs. Because phi of x can be any nonlinear function that you discussed last time. So what if we want to be nonlinear in both the parameters and in the inputs? So generally speaking, what if we want to do something like this? Say our h theta of x is anything nonlinear. So let's say theta 1 cubed x2 plus maybe square root in there, theta 5 x4, and maybe square root the whole thing, right? So this type of model could be a lot more expressive, potentially. Right? But we also want to think about how can we make this computationally tractable, how can we make this useful. Okay, so we have some nonlinear model. And by the way, all these notes will be up online afterwards, so if you don't finish writing something, please don't worry about it. It will be up. And if you want to follow along, I should have mentioned this earlier, but there is a template up as well. So it's going to be what I'm writing on, so the blank version. Cool. So let's go back to our nonlinear model now. We can assume that our xi's are in Rd, so some vector of features or inputs, and our yi is some scalar, so just an R, right? This is pretty standard. We've been looking at this type of formulation a whole bunch. And then our h theta is a mapping from our d, which is our inputs, to R, which is the dimensionality of our outputs. So the cost function we're going to think about here for our now nonlinear model is going to look very familiar. So for one example, I we're going to have ji of theta is equal to the square of the difference between the class label and the prediction. So yi minus h theta of xi, and all of that squared. So that's the cost for one example. If we want to get the cost for the whole entire data set, we're going to average. So what this is going to look like is we're going to have j of theta, 1 over n is the size of our data set from I equals 1 to n, and then here we have ji of theta. So this is for entire data set. Okay, so this constant is a little different from before. This is a common convention in deep learning. It's usually this is called the mean squared error, so it's usually the average. The constant really doesn't matter. Your optimizer is going to be the same regardless of what constant you're going to have out front of that sum. Does that make sense? Cool. All right, so now we're going to talk about how do we, oh, yeah, question?
If the constant doesn't matter, why is it there? Like, we're presumably not supposed to make n equal to 1, right?
So n is the size of your data set. So you're just, this is the mean squared error. So you're averaging over all the squared errors in your data set. So the reason the constant doesn't matter is when you take the gradient, your x that's going to result in your minimum is going to be the same regardless of whether it's 1 over n or 1 over 2. You asked, why do we use it at all? Sometimes it's helpful for scaling, but other than that, there's no real magic behind this. It's just a convenient thing to do. It makes sense to average over your errors. Yeah, it's a nice way to scale things.
Thank you.
No problem. Cool. So what we want to do once we have this cost function is we want to minimize it, right? One way to do that, we can use gradient descent. And so this notation here, we're assigning, this is kind of like coding notation you can think of. We're assigning the right side to the left side. Okay, can anyone tell me why this is gradient descent, what is written here, and not like stochastic gradient descent? What makes it gradient descent? Yeah.
We're using the whole data set.
Yeah, exactly. So you're considering the whole data set here. And the reason for that is if we write out what's actually going on here, our j of theta is, so that 1 over n is here, and we have I equals 1 to n over ji, ji of theta. Right, so we're reasoning over the whole data set. So each update here considers the entire data set that we have. Cool. All right, so here's stochastic gradient descent. So the idea here is we're considering now only one single example every time we update theta. Right, so we have some hyperparameter alpha. Alpha, same as for gradient descent, some number greater than 0. We're basically initializing our parameters theta randomly at the start. And then we go through some number of iterations. We sample some example from our data set, and we do this with replacement. And we continue on until either we converge to something we're happy with, or we reach our maximum number of iterations. So this is with replacement. I'm going to briefly sketch out what SGD usually looks like more commonly in deep learning settings, just so you guys have an idea. So this is one variant. Here is going to be another one. And so the variant that's in algorithm 1, that's going to be in your notes. This other one is not. But I just think it's helpful to know some of the terminology when you go into the foray of deep learning as well. Okay, so we go through a for loop where, let's say we're indexing at k. We have 1 to n epoch. So epoch is basically a term to mean you've gone through your entire data set. And so in deep learning, you'll often see, or if you read deep learning papers, you'll see, oh, we trained for blah number of epochs. That's what that means. That's how many times the optimization has basically gone through the data set. So for k equals 1 to n epoch, we can shuffle the data. And then for j from 1 to n iter, here we might not have enough time or desire to go through the entire data set. So maybe we decide that we want to go through 500 examples out of the data set and call that an epoch. That's also fine. So we have for j equals 1 to n iter, we're doing the same type of update. And here we have no replacement in this inner for loop with the j index, because we don't want to look at the same example twice in the data set. Does this make sense? Yeah.
So I guess the only difference is that with replacement or
Yeah.
not replacement?
Pretty much, and slightly different terminology. Cool. Yeah.
About the K thing. So you basically like having this number of iterations. By n epoch, you mean like n times one epoch, or like one epoch in itself? Like if the data set has n samples, then are you going from k to 1 to n? Or are you going from k to 1 to like n times and this other?
The latter. So the question is, what does an epoch mean? And basically, it's if you go through the entire data set, it's how many times you go through the entire data set. Any other questions here? Cool. I'll talk about the last version of gradient descent for today, and this is mini batch gradient descent. So with mini batch gradient descent, the main difference is you're considering B, or a batch number of gradients at a time. The reason we want to do this is with things like GPUs and parallelism, this actually speeds up computation. So we can compute B gradients at the same time or simultaneously, as opposed to doing them sequentially, and that can be quite a bit faster. So let me write out some of that. So we're computing B gradients, and they look like maybe grad J, J1 of theta, all the way to grad JB of theta. And we do this simultaneously. Cool. So one question you might be thinking about, how do you choose B? And very often you choose B empirically. So you test things out, you look at your validation set, things like that. And you'll talk about evaluation a bit later as well. But one way to choose B is choose the maximum B that your GPU memory can handle. And that's sort of a good way to speed up what you're doing. But the trade-off is usually, and this might come up in your homework as well, usually the lower the B, the better the performance of the algorithm. And I'm not going to talk too much about why this is the case. This is also active research, but just to give you some idea of how folks go about choosing these numbers. So, any questions about mini-batch gradient descent? Yeah.
I guess it's exactly the same as normal gradient descent, except that you're just doing this entire thing over a batch as opposed to the whole data set. Right?
Yes, yes, precisely. Any other questions? Yeah.
I have a question about replacement and replacement. Is that,
Yeah.
what does that exactly, what does with replace this?
Yeah, so with replacement means, say we picked example 2, we can pick example 2 again in the future. Whereas without replacement, in the corner case, it means if we picked example 2 within that J for loop, we will not pick example 2 again until we get to the next epoch.
So in example 1, you can have multiple.
You're just randomly choosing one example. It can happen to be the same example, it cannot. Does that make sense?
Do you go through the entire data set, or do you just randomly?
In the middle one, you randomly pick examples until you reach an iter. Whereas in the left one, you're more trying to go through your entire data set and then do that again. Any other questions on anything gradient descent related? Yeah.
So for the mini batch case, we actually do not. There's no variant with replacement.
So with the mini batch, no, because you're considering, say your batch size is 10 or 64 or whatever. You don't want multiple examples in that to be the same. You want all the examples to be different.
But between batches, do we replace these elements back to the stack?
Between batches, you can, yeah. Sometimes you don't, sometimes you do. It's sort of like a design choice, but you can. In this case, when it's saying without replacement, it means that within one batch, you don't have doubles.
Thank you.
Yeah, no worries. Other questions? Okay. All right. So next, we're actually going to define some neural networks. So we talked a little bit about how we optimize these things, but we didn't really get into, for example, well, how do we define the neural network yet? Or how do we compute the gradients, right? Like when we talk about multiple gradients, how do we actually compute these things? And we need to be able to do this in a way that's computationally efficient. And progress in machine learning really took off in the last 10, 20 years because of advancements in hardware, because we were able to parallelize on GPUs and make these things so much faster, and also algorithmic developments as well, of course. Cool. So we're going to talk about neural networks today and how we define them. The backpropagation, which is how do we compute these gradients, that will be covered next lecture. Okay, So this example came up at the very start, I think maybe first lecture or something like that. But the example here, we're looking to predict housing prices, right? And we looked at how we can do this with linear regression, with linear models. And say with our linear model, given the size of a house, we have some data where we have some, size and prices, and we can plot them on this plot. And our model maybe looks something like this, with something like linear regression. Okay? What's a problem with this? Why might this not work so well? Any thoughts? Yeah.
Maybe something non-linear predicts it better.
Yep. That's a good first one. So prediction might have a non-linear relationship with the input, right? And we only have a linear model, so maybe that model doesn't capture the relationship that well. What's another reason this is not great?
Prices can't be negative.
Sorry, repeat that?
Prices can't be negative.
Yes.
Shouldn't go to infinity.
Yes, exactly. The second issue with this is that prices can't be negative. And when we have a linear model like we do, they can, right? Nothing's preventing them from being negative. Can anyone think of like the simplest thing you can do to fix this problem? Yeah.
You can fix the intercept to be 0.
Sorry, say that louder.
You can fix the intercept to be 0.
Yes, you can fix the intercept to be 0. So what does that mean for negative numbers? So fixing the intercept to be 0 would be this, right? Yeah.
Yeah, the whatever house with negative price will have negative size, which also doesn't make sense. So.
Yeah, so one thing we can do, let me write out these issues first, but I'll show you a solution in just a second. Does anyone know a function that can fix this for us? Sorry, say that louder. Okay, any other ones? Yeah, ReLUs. Has anyone heard of ReLUs? One person, a few? Okay, so we're going to talk about ReLUs in just a second. Okay, so the issues that we talked about here are the prediction might have a nonlinear relationship with the input. And the second issue is we can have negative prices. Okay, so what we want our ReLU to look like, or what we want this function to look like, is something like this. So basically, for all things that are in the negative side, we map to 0. So that's what our ReLU is going to be. And what that looks like in math terms, we have our regular prediction, but we want the maximum between what linear regression would output as a prediction and 0. And then our parameters here are going to be W and B. So this is ReLU. This is how it's usually written. And this is the notation that we will use. So you can say that ReLU is a function of t here. And then really we can just write our prediction as this ReLU function, which is Wx plus B. And does anyone know what ReLU is? What it's called in deep learning terms? Yes?
What's the point of linear unit?
Yeah. Any other, so like what category of functions is it in deep learning? Yeah. Exactly, activation function. So our ReLU is an activation function. Can anyone tell me, is ReLU linear? Okay, raise hands if you think it's linear. Okay, nonlinear? Yeah, it is definitely nonlinear. The maximum creates our nonlinearity there. Okay, so this is our nonlinearity in deep learning, or often is. It's also sometimes called one neuron. Okay, so going back to our housing price prediction setup, yeah, question?
Question about activation functions. Are they all supposed to be nonlinear?
Yes, activation functions are by definition nonlinear. We'll talk at the end a little bit about what happens if they are linear. Other questions? Cool. All right, so let's set up our high dimensional input example. Right, so far we've, especially in this plot, we've been looking at one input, one output, so scalar to scalar. So what if we have more features, so high dimensional input? And this is the case when we have x be in RD and y be still scalar. So we're still predicting housing prices, for example. So our new terminology for our prediction is ReLU of WTX plus B. Okay, and so our x is just going to be stacked features or inputs. So we have x1 all the way to xd. And this is in RD. And then our weights, our weight vector, W is going to be in what dimension? Can anyone tell me, based off of how I've written it? D, that's right, because we're making a dot product with x. And then our B is called our bias, and it is going to be scalar. What we want to do in deep learning is we want to stack these neurons. So output of activation functions is going to be the input to the next one. And this is what creates that expressivity of deep learning models. Basically, they have a bunch of nonlinearities that are stacked one on top of the other. And this becomes a super flexible framework that can represent a lot of different domains. Okay, so now let's make the housing price prediction problem a little bit more concrete. So let's say our x is going to be in R4, and say besides size or square footage, which is x1, we're also going to consider things like number of bedrooms in the house. What's another thing? Maybe we can consider the zip code that the house is in. Maybe it's close to a subway or something, right? And the last thing we'll consider is maybe something like wealth of the neighborhood. So these are our features or inputs. And what we might want to do is compute some intermediate variables. So what I mean here is maybe there are some things that combine some of these ideas and help us make a prediction for what the price of the house might be. So one example is maybe the maximum family size that a particular house can accommodate. So what would the maximum family size potentially depend on? Out of the 4 inputs that we have. Yeah.
Size and number of bedrooms.
Size and number of bedrooms, yep, I would agree with that. So we can also think of other variables like maybe how walkable the neighborhood is, and that might depend on the zip code, for example. And the last one is maybe school quality in the neighborhood that this house is in. And this will be our A3. So A1 through A3 are some intermediate variables that we think might be helpful to make predictions about housing prices. Okay, well, so how could we maybe write these out in terms of math notation? Well, let's use our ReLUs that we just found out about and do ReLU of some linear combination of the features that we think might make sense in this context. So maximum family size, maybe we have combo, like someone said there, of the size, which is x1, and then maybe we add the number of bedrooms, which is x2, and we have some bias term, which is going to be theta 3 here. So theta 1, theta 2, theta 3 are all parameters. And then we can do the same thing for the rest of these intermediate variables. So we can say theta 4, so walkability depends on x3, which is zip code. And then we have another bias term. And then finally A3. So we have ReLU of theta 6. So A3 is walkability. Maybe that depends on A3 is school quality, so that depends maybe on zip code, which is x3, and maybe on wealth of the neighborhood, which is x4, and then we have some bias here as well. Okay, so these are the intermediate variables that we think might be helpful here. Okay, and the last thing that we might want to do here is let me just change this notation so it's not confusing for the notes later. These are all W's, and the biases are going to be B's. These are B2s, B1s, make sure. Oh, sorry. Okay, no, I actually had it right the first time. Ignore me. So these were all theta parameters. At the end of the day, it doesn't matter. I just want to make sure that it matches your notes so it's not confusing later. So 1, 2, 3, theta 4, theta 5. Okay. So this is actually one layer that we defined here. Okay? And finally, once we have these intermediate variables, we're actually going to make the output. We're going to construct the output, right? And our output is our h theta of x, which is going to be, if we follow this construction, we're going to write ReLU of, and here we're going to make combinations, a linear combination of these intermediate variables A. Right, so we're going to have theta 9 A1 plus theta 10 A2 plus theta 11 A3 plus theta 12. Okay? One thing, so this is going to be our end goal or end prediction here. One thing that usually happens in deep learning is we actually, for the output, we don't use a ReLU. So it's sort of like convention. Nothing is necessarily stopping you from doing that. It's just by convention, usually we just have a linear layer at the end. Cool. So now that we look at this diagram that's here on your right, so we have all the things that I talked about, right? We have the size, the number of bedrooms, the zip code, the wealth, and it's going into these intermediate variables, right? So this is A1, A2, A3, okay? And the weights that we're considering that are relating, sort of taking from the first set of inputs, X, to A. So for example, here we have theta 1, here we're gonna have theta 2, and so on. Does this make sense? And this structure that sorry, question?
Sorry, I had a question about the dimensionality of the weights.
Right now, they're all scalar. Everything we're talking about right now is scalar. So whenever we have the subscript, it's usually scalar. Yep.
Here you are like having a few intermediate variables, and towards the end, you're just using those intermediate variables. But
Yes.
it's possible that some of those original variables might still be useful.
Yes.
So is there any way you can kind of transfer them over towards the end or something?
Yeah, I mean, if you look at A2, for example, if you set say this is X3 is positive, and you set theta 4 to 1 and theta 5 to 0, then you transfer over all the information from X3. Cool? Okay, but this structure, we came up with this structure based off of our knowledge, right? This was not something that was determined by some algorithm, we just came up with it because it seemed to make sense. So this is called prior knowledge, and infusing your model with it, basically. But what if we want to be a little more general? What if we don't want or don't have the prior knowledge to do this in a way that results in good performance? So this is getting into something called fully connected neural network. And what this means is we no longer think about these ideas of family size, walkability, school quality. We don't know what those intermediate variables might be, but maybe they depend on all of the inputs. So each intermediate variable will depend on every single input. So this is going to get messy, but I'll try to use different colors. So every single variable here will depend on all the ones that came previously. And this is a much more general way of thinking about this, right? We don't have to infuse this prior knowledge into the system. We can let the neural network figure it out. So what this looks like mathematically is maybe we would have like A1 be equal ReLU of some weight x1 plus some weight x2 plus some weight x3 plus another weight x4 and plus a bias term. And we can do this for A2 and so on and so forth. Does that make sense? Cool. So what this looks like, if we start looking at vector notation now more, this might look like this. So we have A1 is equal to the ReLU of W1. This higher index notation in square brackets is going to refer to layers. So this would be the first layer, and this would be the second layer in this network. So we have W1, layer 1, transpose with all the inputs x. Now this is a vector. So now we're doing a dot product. And we add some bias term. Okay? Can anyone tell me what dimensionality W1 in the first layer is? Yeah.
4.
Yes, that's right. And that's because our x is dimensionality 4, and our bias is still a scalar. Okay? And then we can do the same thing. We can say this, still first layer. Okay? And the last one, same thing. Okay. And then finally, we have our prediction. And the prediction now is going to use weights from the second layer. And it's going to operate on those intermediate variables A. Okay, so we're going to have W2, and here we have B2. And now W2 is going to be of what dimension? Yeah, I heard it somewhere. Yes. Because A is of dimension 3 here. And the bias still scalar. Okay, so this is a 2-layer neural network. And this is the same thing as saying we have one hidden layer. So intermediate variables are referred to in deep learning as hidden units, and the associated layers are hidden layers. Okay, any questions on that? Yeah, yes. Great question, great question. So you're going to be limited by compute, but aside from that, it's a lot of experimentation. So for example, GPT-3 has a lot of layers, but it's also dealing with a lot of data. If you have just a little bit of data and just a few examples, you probably don't want to use a very big model. And I think you'll talk a little bit about why shortly. Any other questions? Yeah.
What's the difference between all the different hidden units if they're all relying on the same input?
So the hope is that the network learns different representations, but technically nothing is really stopping it from exactly what you said, just replicating ideas, but it often doesn't. And it's trying to learn these A's in the best way that can help the neural network make a prediction H theta of X, right? So this ends up working actually quite well. Yeah?
The dry knowledge example, you had some meaning in the but we use this kind of, when you fully connect the neural network, then moving to like the hidden layers, is there any like inference from the...
Yeah, so that's actually an active research area as well. It's called interpretability in deep learning, and either figuring out if there is any, or figuring out how we can induce there to be some level of prior knowledge, so some interpretability. I think there's a question at the back, yeah?
So just to double check,
W
is the weight
Yes.
you're going to be applying to
That you're going to be applying to what?
the X is the
Yes, so W are the weights that you're going to be applying to the X's, and then W, so those are W1 with the square bracket at the top, and then W2 with the square bracket at the top is going to be the weights you're applying to the A's. Yep. All right. Okay, so this is some notation. Yes, question?
Question, which is more generally, yeah, I kind of get the sense that if we get rid of the values, everything is just linear. And so
Yeah.
what's the point of the neural network versus just a regular linear regression?
Yeah, so that's a great question. You're completely right. If you get rid of the ReLUs, things are just going to be linear. The ReLUs are what make the neural network be more expressive. So those nonlinearities, those activation functions, are really the heart of the neural network. Okay, cool. I'm going to move on in the interest of time. So we have a two-layer neural network, and we just talked about all these things. The only difference here is that we're changing notation a little bit. So we're introducing the Z, which is just a linear combination of X's with our weights and our biases. And then we still have our A's. The number of A's here is M. So this is the number of hidden units that we're considering. So we had 3 in the last example. More generally, we'll have M. And then, yeah, otherwise this is exactly what we just wrote out before. Does this make sense to everyone? Any questions on this? Okay, so we're going to talk about vectorization. We're going to make this even more vectorized, right? So we had like a lot of notation, a lot of indices here. We want to get rid of as much of that as possible. One, to make things cleaner and not have to write all these indices everywhere. And 2, which is the more important reason, vectorization actually makes things faster. It makes things better able to be parallelized on, for example, GPUs. So what we can do first is think about those weights in our first layer, right? Those W's with a square bracket 1. And what we can do is we can transpose them, so they're rows, and stack them in a matrix. And so what we're looking at here is M by D. So M is our hidden unit dimension. And D is our input dimension. So these are all the weights in our first layer. And then what we can do is we can actually write out those equations from before in this vectorized form, where, for example, we can write out Z1. If we take the first row of this, Z1 will be W1 of 1 transpose X1 plus B1, 1, right? Which is that first row that we had before, okay? But this looks way, way nicer, and this is our vectorized notation. Any questions on this? So it's the exact same thing, just more compactly written. Cool. Okay, so now that we have these Z's, this is actually called pre-activation. So this is before we applied our ReLUs. And we have these Z's. This is capital W. I'll do it with those little bars at the top. And it's all our weights from our first layer. We take the X and we add our biases, which are also stacked together. And all of this is going to be of dimension M, which is the same dimension as our hidden units. Now, we want to get A's out of this. And to do so, we need to apply the ReLU to every element in the Z vector. So our A's are A1 through AM. And we want to apply ReLU to each one of these Z's. We're actually going to abuse notation here a little bit. And we're just going to write this by definition to be ReLU of Z. So it's an element-wise operation. And we're going to refer to it the same way as we would for a scalar. okay? And then what we can do is we can write our second layer weights. In the second layer, we only have a scalar output that we want. So we only have one weight vector to include here that we're going to transpose to be a row. And this is going to be in dimension 1 by m. Any questions on that part? Okay. And we're still going to have our bias in the second layer, which is still scalar. And so our final output here is going to be this W2 matrix times A, dot producted with A, and the bias term. And what I said before is that vectorization helps us parallelize things on GPUs. Okay. So we talked about 2-layer neural networks. What if we have more layers? So notation just follows, right? So before we stopped with one hidden layer, which is a 2-layer neural network. And now we're going to have R-1 hidden layers, which is an R-layered neural network. And like I mentioned before, so all the hidden units will have ReLUs, whereas the hidden layers, whereas the prediction, just by convention, will not. And we'll refer to these big W's as weight matrices. And these bias terms will just be called bias. Nothing really changed. And these A's will be hidden units. One thing to note is the dimensionality of these A's, right? So what is the dimensionality of A, K? So A, layer K. And that's going to be, we're going to refer to that as MK. Okay? And so can anyone tell me what the dimensionality is of W layer 1? Sorry, say that louder. D cross K? What do folks think?
I think it's the other way around.
So it's K cross D? Is that looking? Yep. Yes. 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 There we go. Okay. So it's M1 cross D. So D is our input. So we want this matrix to do matrix multiplication with X. X is of dimension D. So we want that last dimension to be D. The first dimension is the dimension we want as the output. The output will be A1. A1 is of dimension M1. Does that make sense? Okay. And then, so just for practice, what would W2 be? Yeah.
Would this be R-layer network or R-1 layer?
This would be an R-layer network with R-1 hidden units. What is the dimensionality of W2? Can anyone help me? Yeah.
M2 cross M1.
Yes. M2 cross M1, because the input will be A1. That's what's being multiplied with W2. And the output will be A2. So we want M2 output. Okay, cool. And so this can more generally, we can write this for WK. We're going to have our mk cross mk minus 1. And bk is just going to be mk dimension. Any questions here? No? Okay, awesome. So we got this question earlier. Why do we need an activation function ReLU? Can anyone remind me why do we need it? Yeah, so it's our nonlinearity. It's what makes what we're doing here nonlinear. But for fun, let's see what happens if we don't have the ReLU at all, or we have it be just identity. So this is a 1, sorry. Okay. So we have our hidden layer A1, and then say we only have one hidden layer. So our output here is going to be W2 of A plus B2, okay? And then if we actually substitute in for A1, what are we going to get? So we're going to have W2 of W1 X plus B, okay? All of that A, oh sorry, that was A, plus B2, right? And then we can actually expand it out, and we're going to get, watch my math so I don't mess this up. We're going to get W2 W1X plus W2 B1 plus B2. So what does this really look like? Well, we can define these to be, say this is W tilde, and say this is B tilde, right? The second term doesn't depend on X at all, and the first term does, okay? So this is just a linear function of X as we would have in linear regression. Essentially, everything would collapse, and we're here linear in these parameters. Any questions about this? So if we lose the ReLU, we lose the nonlinear expressivity of the neural network. Yep. Yeah, you can definitely have other ones. So in the notes, I think we mentioned the sigmoid activation function and the tan-H activation function. I would probably say ReLU is the most common, but it really depends on your application, the kinds of outputs you might want, things like that. There are definitely other ones, and there's also, besides just the kinds of outputs that you might want, these activation functions have certain properties when you try to compute gradients with them and things like that. And that's a little bit beyond the scope of this lecture, but if you have questions about this later, come by, and I'll be happy to chat. Any other questions on this? Yep.
On that note, like, if you look at it, ReLU is perhaps the closest to what we can call as a linear activation function, right?
Yes.
So why is it so commonly used despite it being quite close to be, not quite close to be?
It works well. Yeah.
Why are you calling it the linear in the parameters when it's a linear function of X? So why is it not linear in X?
Oh, yeah, good point. Yes, you're right. I meant it in the sense that the parameters are going to be linear here. Yep. Other questions? Okay. one last new-ish idea I want to talk about, and that is connection between neural networks and kernel methods. So kernel methods, we talked about this very briefly at the beginning of this lecture. So the kernel method output or prediction is going to look like h theta of x, theta transpose phi of x. So we're linear in parameters here, but not in x. Yeah? Everyone agrees? Okay. So looking at that penultimate layer, AR minus 1, what if we write it as phi b of x, where, phi beta, where our beta is going to be all our parameters. So our parameter is W1, all the way to the penultimate layer, WR minus 1. And also our biases, which are 1 all the way to BR minus 1. Okay, and then we can write the prediction from our neural network as W of R, so our last layer, matrix multiplied with phi beta of x if we fix our parameters. So we're fixing beta here. And we can add our bias term. Okay? So really this looks pretty much the same, right? The only difference is within the neural network, phi beta is actually learned. So the algorithm is looking for the best possible features for this data. Whereas in the kernel methods, we choose the kernel. So there's more of that prior knowledge and prior structure that we're infusing into the algorithm. Whereas here, there's flexibility in that these phi beta parameters can actually be learned to best fit the data. And because of this sort of structural similarity, the penultimate layer output, AR minus 1, is sometimes called the features or the representation. Within a neural network. And so if you ever hear terms like representation learning or something like that, it's talking about those hidden layers within the neural network and what we're learning there. Any questions here? Yeah, at the back.
That line where you say h theta of x equals WR phi or b beta, that's all supposed to be one line, right?
Yes.
Okay. So the whatever that Greek letter is called is the only subscript.
So it's WR matrix multiplied with phi underscore beta of x plus all of that plus the bias term BR.
Is the plus the bias term of R part of the? It's not like a subscript at all. It's
no.
Okay, thank you.
Yeah, sorry. Other questions? No? All right. So today we talked about two different things. We talked about supervised learning with nonlinear models. And what that might look like, what the cost function looks like. And the second thing we talked about are neural networks. How do we construct them? We first started with 2-layer neural networks and then expanded that notation to be R-layer neural networks. And next time, Tengyu is going to talk about backpropagation. So how do we actually optimize? How do we perform stochastic gradient descent or any kind of gradient descent in this framework? So how do we compute the gradients for the cost function and for the neural network? Any last questions? Okay.